R squared is called the coefficient of determination. I go back and forth with the subscript and writing it as is. This time I'll do it that way. I am going to move, let's see. Good. And I will divide both sides by SSE. Do you find any of that to be, for can I say, relevant? Does it make any sense? You are looking at a proportion of the total variability relative to error. Total regression from a squares relative to error. Doesn't make much of sense. Yes? So you can rewrite this expression any way you want. It has to make sense. So how about I keep SSR on this side and move SSE. Good. If I divide by SST on both sides, I will have SST divided by SST minus SSE divided by SST, SSR divided by SST. Agreed? And you will have 1 minus SSE divided by SST equal to SSR divided by SST. With me so far? Of the two, I would say this makes better sense. Do you agree? I'm looking at what percent or what amount of variability relative to the total is explained by one model. And I'm setting that equal to 1 minus 1% of error that I have relative to the total. So of the two, this makes better sense. So R squared good. Well, do I want that to be large or small? Large. And how large could it get? Well, right? Ideally speaking, if that is a perfect model, the fitted value and the actual value would be one and the same. Yes? If they match up perfectly for every single observation, all residuals will be 0. Sum of squared residuals will be 0. That part will be 0. Yes. If that becomes 0, R squared is 1. You've got the perfect model. That's not going to help. Shouldn't have to take it. If it gets closer to 1, then you have a significant model. SSE in this case, what would 1, 2, 28.8. And SST 12, that's 9.24. What do we get? Point 9.8%. So 976. That's at 16. So I guess the number 0.9768. Anyone can come up with a number. I can't do it. How do we interpret that number? Well, this tells us, before I make that conclusion, do we agree that there is variability in the y values that you observe? Do we agree? Because there is always noise error on the same. So R squared of 0.9768 gives me conclusion that 97.68% of the variability in y, the observed y, is explained by x. Good. So whatever things, variations that you see in y, about 97.68% can be explained away using x. In other words, I can explain the amount of money that you spend per week on food using the number of times you eat out at a restaurant. But I can only do it, explain it up to 97.68% using that one predictor. Does that make sense? Well, if I can explain 97.68%, what goes unexplained?
0.32%.
Well, now where is that 2.32%? Or what does that correspond to? So we have tried our best to model all the changes that we see in y and explain away 97.68%. Still, there is 2.32% of variability that I'm unable to explain. In other words, there is always some random thing happening which I cannot explain using this model, which is why I say there's no such thing as 100% in statistics. I have someone for an interview and someone said, I'm 100% certain about this data, I will not get a job. Because it defeats the purpose of stats or any data science for that matter. So this number is explained variation. In y. Take a guess, what will that be? Unexplained variation in y. Add them together, what would you get? Total variation in y. The difference between r squared and what we had earlier, this is not a percent. those are just amounts. R squared, on the other hand, makes it relative to the total variation. Does that make sense? So that's all we're saying. Here we are getting a percent. There, it's just explained for total variation. You can split that up. Something that can be explained using the regression. And a tiny bit that you cannot explain. There's always noise. We want that unexplained variation to be big or small. We want it to be small. And you can trace this logic back. If SSE becomes small, MSE becomes small. Do you agree? If MSE becomes small, then the F ratio or F statistic, which is the ratio of MSR divided by MSE. So you take any number and you divide it by a small number, what would be the result? Would it be small or large? Large. And if F is large, what would happen to the p-value? It's going to be small. If the p-value is small, you would end up concluding model is significant. So connecting all the dots. So we use linreg using the calculator with the function linreg to fit the model and have the data x values list 1, y values list 2. By default, the calculator is going to treat the first list as x, second list as y. So start over to calc option number 4. You don't have to specify anything. If you hit enter, the calculator is going to assume the first list is x, second is y, but you can be specific by typing second 1 over second 2. And that would give me A, the slope to be 11, B, the y-intercept to be 41.2. R squared is 0.9768, and R is 0.9883. What is R? Correlation, we're missing the word coefficient. So R is the linear correlation coefficient, and R squared is the coefficient for determination. Just squaring makes a huge difference in interpretation. Do you agree? So if you are using R squared, this is how you should interpret. But if you're looking at R, what would you say? You look at 0.9883. It measures the amount of linear correlation between x and y. Do you agree that there is a good strong correlation between x and y? Yes. Is it positive or negative? Positive. So the strength of correlation is 9.9883. But R squared is not looking at the data, rather it is looking at the fitted model. Either. So R would be the very step of regression analysis. You plot x and y, you get a scatter diagram, and you're looking at it and you're saying, oh, I have a relationship. We did this. And that would be the first step. R squared, on the other hand, is the last step. R squared uses the model to tell us, how significant or how good of a model we have. And naturally, if R is bigger, R squared will also be, I should say bigger. If R is close to 1, R squared will be close to 1. If R is close to -1, R squared will be close to 1. Don't say -1, it's squaring 1. Are we clear? R squared be clear? Okay.